Recording. Okay, so I think we're starting the recording. So now I want to talk about Riemann-Hilbert correspondence again. Um, so far, first I want to review what we've done so far, a little bit of what we've done. So the Riemann-Hilbert correspondence is an equivalence of three categories. So we have holomorphic connections on one side. Oops, yes, I knew that was going to happen. Okay, let me make a mark here. Okay, so we have holomorphic connections, and we have complex local systems, and we have finite dimensional complex representations. So let me start with an example of this equivalence. So we started with this example last time as well. So we can start with the linear ordinary differential equation with singularities. So here we have f prime is equal to f over 2z, and the singularity is at z equals 0. So then I'm going to take my domain to be d is going to be c minus 0. So now the coefficients of this ODE are holomorphic functions on the domain. So this is a first order linear ODE, and n is equal to 1. N is going to be the order of the ODE. So now I'm going to go through each of these categories and say what the object is in each of these categories corresponding to this ODE. All right. So first, what is the object in the category of holomorphic connections? Right. So a holomorphic connection is going to be a pair. We have this thing and this thing. So these are two symbols. So what is the first one? This is a sheaf of holomorphic functions on D. So again, D is my domain, it's C minus 0. And the sheaf of, okay, so OD is just going to stand for the sheaf of holomorphic functions on D. So for each open set of D, my sheaf is going to be all of the holomorphic functions on that open set. Okay, so so the information of a holomorphic connection is going to be this pair where the first thing is what's called a locally free sheaf, and the sheaf of holomorphic functions is a locally free sheaf. It's also free, but we'll get to that later. And a connection map is this triangle delta, and it's a connection map for this sheaf of holomorphic functions. And what it's doing is okay, well, so my ODE again is f prime equals f over 2z. And the connection map takes sections of my sheaf, takes sections of my locally free sheaf. So in this case, it takes sections of the sheaf of holomorphic functions on D. And what it does is it gives me one forms. It gives me a one form on D. So the connection map takes a section. In other words, it takes a holomorphic map or a holomorphic function on an open set, and it gives me this one form. And the specific one form it's going to give me is this. And so it looks like my differential equation, but it's df minus f over 2z times dz. Okay, so that's this example of a holomorphic connection. It's a locally free sheaf and a connection map. And the connection map is taking sections of my locally free sheaf and spitting out holomorphic one forms on my on my open set or domain. Okay. So how do I go from holomorphic connections to complex local systems? So in this example, I have this holomorphic connection, which is the holomorphic functions on D, and this particular connection map, which takes sections in here and spits out one forms. And I'm mapping it to the complex local system, OD triangle or OD del. And this is a subsheaf of the holomorphic functions on D. And it's a subsheaf consisting of horizontal sections. So a horizontal section is just a section of is just a local section in my sheaf. So it's just in this example, it's just going to be a function defined on an open set, a holomorphic function defined on an open set, such that the connection map evaluated on this section or this holomorphic function is 0. In this particular example, this is my connection map. And so del of f is equal to 0 if and only if this right-hand side is equal to 0. Well, what that means is that df is equal to f over 2z times dz. So this is an equality of one forms here. And remember that or df is just f prime dz. So on the left-hand side, I have a coefficient times this one form, this coefficient function times this one form, and on the right-hand side, I have this coefficient function times this one form. So both of these coefficient functions must be the same. And so what I get is that this is equivalent to saying that f is a solution to the ODE that I started with, right? So this is how I go from holomorphic connections, which are, so I didn't define holomorphic connection. I just gave you an example of a holomorphic connection here, and how I went from this example of a holomorphic connection to a complex local system. It's the same process of going from a differential equation to the local solutions of the differential equation. So I write this here. F is a local solution to the ODE. So the information of a holomorphic connection is about the same information as an ODE, except so this is the example we have here. We took an ODE and we got a holomorphic connection associated to that ODE. But when we see the definition later on, and I explain it a little bit, we'll see how holomorphic connections are a bit more general than ODEs. So if your locally free sheaf is actually free, then the holomorphic connection can be represented by an ODE everywhere on the domain. But if your holomorphic connection, or if your locally free sheaf is only locally free, it's not free, then since it's only locally free, it can only be represented locally by a differential equation. So that's kind of the difference between holomorphic connections and ODEs, is that holomorphic connections are kind of like locally they look like differential equations. And this map that goes from holomorphic connections to complex local systems, at least in this example, it's taking those ODEs. Okay, so in this case, we have a free locally we have a free sheaf. And so the corresponding sheaf of horizontal sections is going to be the local solutions to the ODE. Okay, so maybe that didn't make a lot of sense, but it will make more sense as I give more concrete definitions. Right now, I'm just giving you an example. So in this example, this sheaf of horizontal sections, it looks like a one-dimensional vector space over each open set. So over each open set, the solutions to this differential equation is, like I solved last time, is a constant multiple times the square root of z. You can solve this differential equation using separation of variables. And so this is a one-dimensional vector space. So when we get into the definition of a complex local system, what it is it's a locally constant sheaf of vector spaces. Right. So here we see that it is a sheaf of vector spaces here. Okay. So that's how you go from holomorphic connections to complex local systems. Again, we're taking my holomorphic connection here, which is, in this example, it's the sheaf of holomorphic functions and this particular connection map. And what we're doing is we're solving this equation, del f equals 0. And solving this equation is kind of the same thing as solving a differential equation. So what we get on the other side is a complex local system, and it is the, in this example, it's the local solutions to, it's a sheaf of local solutions to this ODE. Okay, so that's the example, how it works going from this circle to this circle. So that way. So wait, are there any questions so far about these examples?
It's okay.
Okay, good.
Yeah, this is good so far.
All right. So now reviewing how to go from complex local systems to finite dimensional complex representations. So we did this, I think I was clear about this last time. So here we have a fundamental group of the domain D. So my domain is C minus 0, and the fundamental group is the fundamental group of C minus 0, which is generated by one loop, and that is gives me a fundamental group which is isomorphic to the integers Z. And we have this thing called a monodromy representation, and that is the object in this category, right? So what is happening here? It's going to map the non-trivial loop to -1, and the way you get this representation is by analytically continuing the local solutions, C times square root of Z, along this non-trivial loop to obtain another local solution around the base point. And the difference between the original one you started with and the last one that you got is a scalar multiple of -1. So what it's doing is giving you a representation of the fundamental group where the vector space is the local solutions around the base point, or more accurately, it's the stock of local solutions at the base point. So it's the vector space of germs of local solutions at the base point. And what it's doing is it's taking a germ, analytically continuing it around the non-trivial loop, and giving you another germ of a local solution. And so that's a linear transformation of this vector space, this stock, which is a vector space. So that's how you go from local systems. A complex local system has a stock, which is a finite dimensional vector space. And then what you get is a representation of the fundamental group just by seeing how this local system, the stock of this local system, transforms. Okay, so we are, so all right, so these are the three categories: holomorphic connections, local systems, and finite dimensional representations. And we did cover oops, this is, so we did cover disequivalence, and that's built out of composing some equivalences of categories we saw earlier in the section or in this chapter. And now I want to talk about the holomorphic connections and how they are equivalent to complex local systems. So first, I think it's better if I give the abstract definitions first and then try to convey the intuitions after, because if I try to convey the intuitions, it might be confusing about what we're even talking about. Right. So first, I'm just going to present the abstract definitions and also review the ones before. Right. So we have D is a complex, is a domain in the complex numbers, and it's going to be connected, locally simply connected domain. So we just need these conditions in order to apply the equivalences of categories that we know about covers and pi1 sets, and get the equivalence that we want about local systems and pi1 representations. Okay, so anyway, so finite dimensional complex representation of pi1d is just going to be a group homomorphism from the fundamental group to GL and C. So this is a group of matrices, n by n matrices. N is the dimension of this. So we're saying finite dimensional complex representation. The dimension is this n here, the size of the matrices. So in the example above, n is equal to 1. So GL1C is the multiplicative complex numbers. Right. Okay, so now reviewing the definition of complex local system on D. So all this is a locally constant sheaf F of finite dimensional vector spaces. Right. So the stocks of this local system are also going to be finite dimensional vector spaces, and each stock is going to have the same dimension. So this common dimension is also called the dimension of the local system. And in our example above, we saw that my local system, the object in the category of local systems, is going to be this vector space. So it's going to be a sheaf of finite dimensional vector spaces. So for each open subset of my domain, I should assign it a finite dimensional vector space. And the vector space I'm assigning it is this vector space of local solutions of my ODE on that open set. So this square root of D is interpreted as a function on this open set U, right? So this is a one-dimensional vector space. So this is a complex local system on D. And to see why it's locally constant, I guess like you just need to see like so okay, so this is a little bit confusing for me. But yeah, to see that it's locally constant, you just need to see that if you take a solution, then that okay, I'm just guessing here. If you take a solution on an open set and then take a smaller open set, the vector space of solutions on that smaller open set is just going to be the vector space of solutions on the bigger open set restricted to the smaller open set. So I think that is why it's locally constant, but I may be incorrect there. Anyway, so it's a locally constant sheaf, and of finite dimensional vector spaces. So this is a complex local system on my domain B. And the germs of local solutions constitute the stock of this sheaf. So the stock is also a one-dimensional vector space. So if you look at a certain point X inside of this open set, the stock of the sheaf at X is just going to be the germs of these functions at X. Okay, so that's also a one-dimensional vector space. So cool. So these are the objects in the two categories that we covered so far. And now we get to the third category, which is the holomorphic connections on D. And so this actually takes quite a lot to define abstractly. So let's start. So a holomorphic connection on D is a pair. So, all right, let me make a mark here. So it's a pair, E comma delta, where E is a locally free sheaf on my domain D, and delta is a connection map. So I need to explain both of these things. So first of all is locally free sheaf on my domain D. So what is this? So it's a sheaf of O modules E on D, and it's locally free. So we want to understand locally free sheaves on D. So these are a sheaf of O modules E on D is locally free if every point of D has an open neighborhood V such that the sheaf restricted to V is isomorphic to ON restricted to V for some n greater than 0. Okay, so let's unpack this definition. Here, O is the ring sheaf of holomorphic functions on D. So we already saw this before, and I was calling it OD, right? So in my example above, OD is the sheaf of holomorphic functions defined on open subsets of D. So right here, so If you have an open subset of D, then the sheaf assigns to that open subset all of the holomorphic functions defined on that open subset. So I'm suppressing the subscript D here because it's annoying to write OD everywhere. I'm just going to write O, and that stands for OD, which is the sheaf of holomorphic functions on open subsets of D, right? So this is a ring sheaf. What does it mean? Is that this set is actually a ring. You can take holomorphic functions and add them together. You can take holomorphic functions and multiply them together and still stay in this ring of holomorphic functions. So this is assigning to each open set a ring. So it's a ring sheaf. And then O to the n is the n-fold direct sum of O. So what this means is for each open set, you're just taking n copies of the ring associated to that open set and taking the direct sum of those rings. Right. So that's all this is. So you can think of On as just the sections of On are just n tuples of holomorphic functions on open sets in my domain. Okay, so what am I saying here again? I'm saying that a locally free sheaf on D is a sheaf of O modules. I didn't explain what that is. E on D is locally free if every point of D has an open neighborhood V subset of D such that the sheaf restricted to V is isomorphic to O to the n restricted to V for some n. So what I'm saying is locally, my sheaf of O modules, whatever that is, looks like this n-fold direct sum of the ring sheaf of holomorphic functions. Okay, so that's all a locally free sheaf is. And now the technical part is, what is a sheaf of O modules? A sheaf of O modules is a sheaf of abelian groups such that each abelian group associated to each open subset of my domain is equipped with an O module structure. So an OU module structure. So remember I said O is a ring sheaf of holomorphic functions. So each OU is a ring. So to say something is a OU module means I have a ring and I'm considering a module over that ring. So for each open set, I have perhaps a different ring. And then over each open set, E looks like a module over that specific ring.
So you have OU here. You want, or OV, whichever the open set is. Should this first one be EV? A sheaf of abelian groups such that each.
Right. Exactly. Yeah.
Thanks.
Thank you. So such that each EU is equipped with an OU module structure. So an OU module structure is just telling you how to multiply your sections by holomorphic functions. So you need to have this diagram commute, and all it's saying is this note here. It means that you can scale your sections by holomorphic functions. So does that make sense? Right? Do I have the example here? Yes. Here, our example is E is equal to the holomorphic functions on D, which is obviously locally free. Well, why do I say that? Because one, we need to show that it's a sheaf of O modules. Well, yes, this ring is an O module. It's just the O module. It's a trivial O module. Yes, this is an abelian group, but it's also a ring. So it's a over each open set. It is a ring, or it is a module over its base ring, which is just this base ring. And so yeah, it is locally free. It is a sheaf of O modules, trivially, and it is locally free as well because over each open set, over each small open set, it looks like O to the n. Well, it is O to the 1, so that's good. Right. Okay. So our example is really not even an interesting example of a locally free sheaf. It's the most trivial example of a locally free sheaf. And in fact, it's a free sheaf because So, okay, this is jumping too much. Right. Okay. Where was I? Right here. So in fact, it's a free sheaf because right, because what free means is that it like right because it just looks like this. Yeah, it's just and not okay. Maybe it's more clear if I go to a more interesting example here. If E is if globally E is just the n O to the n, which is the n tuples of holomorphic functions, for some n greater than 0. So I'm not looking at local sets. I'm just looking at the entire domain now. And E is called free of rank n. So that's what it means to be free if globally you look like O to the n. Otherwise, we only have locally you look like O to the n. And then E is called locally free of rank n. So that's the difference between free and locally free. A locally free sheaf just is a sheaf that looks like O to the n in small open sets. And the free sheaf is a sheaf that looks like O to the n everywhere. Like as a full global sheaf. Okay, so if E is locally free sheaf on D, it's also, okay, maybe before I go here, are there any questions about this so far? Definition of locally free sheaf?
This is okay with me.
Yeah, it's good.
Okay. And now we just need this fact about this. Locally free sheaf on D is also a sheaf of complex vector spaces. Remember, what does it mean? It's a sheaf of O modules, right? So that means you can scale things by holomorphic functions, but that also means the constant functions are also holomorphic functions. So you can scale things by complex numbers. So it's also a complex vector space. The way you go from sheaf of O modules to sheaf of complex vector spaces, just restrict your scalars to complex numbers instead of holomorphic functions. And the rank of E is going to be finite. That's by definition. But the complex dimension of the vector space associated to each open subset is infinite, is going to be infinite, because, right, I only have that E looks locally like n tuples of holomorphic functions, but this guy is actually an infinite dimensional vector space. Interpret, this is a module over the ring of holomorphic functions, but as a vector space over C, it's infinite dimensional. Because you can produce infinitely many infinitely many functions, none of which are linearly dependent to any sum of the others, any linear combination of the others. Okay, anyway, so that's just that. The difference between rank of a module and dimension of a complex vector space is there. All right, so as a vector space is really huge, but as a module, it's small. Okay, so that's a locally free sheaf on D. Okay, and then a connection map for locally free sheaf E on D is going to be a morphism of sheaves of complex vector spaces. So now remember, this is a sheaf of O modules, which is locally free, but it's also a sheaf of complex vector spaces by what I just said. So I can interpret this left-hand side as a sheaf of complex vector spaces, and I can interpret the right-hand side as a sheaf of complex vector spaces. I'm going to explain what this right-hand side means in a bit. But it's a morphism of sheaves of complex vector spaces satisfying the Leibniz rule. So the Leibniz rule is this formula here. So I can take any section of this locally free sheaf, and I can scale it by any holomorphic function. So maybe I should write this. S is in E, and F is in, maybe I should also be more particular, this is in EU and F is in OU, right? So I can scale any section of my locally free sheaf by a holomorphic function. And what the Leibniz rule is telling us is that evaluating my connection map on the scaled section is going to look like the section tensor product, the differential of the scalar function plus the scalar function times the connection map evaluated on S. So this is kind of like a product rule. And I'll say more about this probably in the intuition section, which I'll get to later. But first, I want to talk about what it even is, this right-hand side. What does it mean? So here, omega D1 is a sheaf of holomorphic one forms on D. So holomorphic one forms, I could define those, but I think I'm not going to. We'll see an example. And the tensor product E tensor over this sheaf of holomorphic functions, this ring sheaf of omega D1 is defined by E tensor omega D1 assigns to each open subset of my domain the tensor product of rings, right? So here, this or tensor product of O modules, or OU modules. Here, OU is my ring assigned to each open set locally, and EU is going to be a module over this ring. Oops. Yeah, EU is going to be a module over this ring, and omega D1 of U, I guess, is also going to be a module over this ring. Anyway, so we have this tensor product of modules over this ring. And then in our example, so let's look at this example, F prime equals F over 2Z example. So this is the differential equation we started with. My locally free sheaf looks like is just the holomorphic functions on D. So this is a locally free sheaf on D. In fact, it's just a free sheaf on D, and its rank is equal to 1, right? So this is n is equal to 1 here. And if we look at the tensor product for this particular example, it looks like I'm taking E tensor the one forms on D. So E again is the holomorphic functions on D. And I'm taking that and tensoring it with the holomorphic one forms on D. And what I should get is just the holomorphic one forms on D again. So remember, this ring sheaf down here is the same one up here. I'm just suppressing the D down here because I said I would. But when I brought up the example again, I reintroduced the notation. So that's why it's a bit inconsistent here. But this is the same thing. This is the same ring sheaf as this one here. And to see that this is actually just the same sheaf of holomorphic one forms, we look at locally each open subset of my domain, and this guy is defined like this. It's locally, it's defined as the tensor product of these things. And so we look locally at this tensor product, and then we do see that this is locally looks like holomorphic one forms again, because I'm taking a ring and tensor producting over the same ring of some module, and that recovers the module, right? This is a general note about tensor products. For any A module M, if I'm tensor producting M with A over the ring A, then I recover M. So that's why this is just the same thing. So in our specific example, the connection map just goes from the holomorphic functions on D, that sheaf, to the one forms on D. And that's exactly what we were doing up here in this example when I first introduced this right here. It takes a holomorphic function and gives me a one form. So that's precisely what I'm getting, right, in this specific example. And the tensor product is just allowing me to understand what's happening if the rank of my locally free sheaf is greater than 1. And when it is just a free sheaf of rank 1, like in this example, then the tensor product is just a holomorphic one forms. But the tensor product allows us to understand or talk about in the same language about more complicated situations as well, right? So if E were free of rank n, so what that means, so now it's not just locally free, it's actually free. So globally, it is looking like n tuples of holomorphic functions. So E is isomorphic to the sheaf OD to the n. And then if you look at what this tensor product looks like, it just looks like OD to the n tensor, the one forms, and that is just going to be n copies of the one forms. So if I have a locally free sheaf, if I have a free sheaf of rank n, then this tensor product is just n tuples of one forms, right? So what is this? What is this direct sum? N-fold direct sum of omega d1. Locally, it looks like n copies of omega d1. So I'm just getting, so on each open set, it's giving me the this guy, which is the product of these one forms, omega 1d. Okay, and indeed, to check that this is true, I don't know if this is valuable to actually go through, but yeah, you just you look at what's happening locally, and then right here we're using the fact that a to the n tensor product m over a, where m is some a module, it is just m to the n. So that's what we're using here, n-fold direct sum of m. Okay, so is that clear?
It's good.
Okay. So but in general, we don't have a free a free sheaf of rank n or a free sheaf of rank 1. What we have is a free sheaf, a locally free sheaf of rank n, right? So what that means is for each point in my domain, there is a small open set V such that my locally free sheaf restricted to that open set V looks like OD to the N restricted to that open set V. And now this is, I say here, I think, because I'm probably, I don't know if every step here is justified, but what it's looking like, I believe, is that if we restrict our locally free sheaf of rank n tensor product with the holomorphic one forms on D and restrict this tensor product to this small open set V on which this holds, then doing this tensor product, see, I don't know if this step is justified, but let's just say,
I think this is how I think this is just how, I might be wrong, how we're defining this sheaf, this tensor product sheaf is defined to be E of V tensor O of V with omega 1D of V. So you're just, I think this is part of the definition of what it means to be the tensor product of sheaves. Might be wrong, but I think this is fine.
Yeah. Okay. Anyway, I don't know. I don't know if this is any valuable to understanding.
What is that you think?
Yeah.
Right. I'm saying, what do you think that you're doing that might not Correct.
I just don't know if this probably like if this O,
I think
if I can put that down there. But
yeah, I think that's part of the definition. Might be of the tensor product sheaf.
yeah, so the definition of a tensor product sheaf is given in this way.
So where U is any open set.
Yeah.
So that's why you have O of U down here.
Oh,
So
okay.
you're choosing a different open set down below.
Right. Okay. Yeah. Yeah. Okay. So this is fine. And so at the end of all this, what do you get? Is locally, I'm just reusing the fact that it's free on this open when you restrict to this open set V, and then reusing this fact up here, we get that locally it looks like n copies of one forms. So that's the point, is that locally this tensor product looks like n copies of one forms on V. Okay, so that's the definition of a connection map, and so we understand what this side is. Now I actually have to talk more. So I want to give an intuition of what the connection map is doing, but at least now all of the definitions are laid down. So now I can go ahead and start talking about intuition. So far, is everything good?
I have one question.
Yeah.
But it's way up above where you're looking at how you define where you have a sheaf above defined where the locally constant sheaf where the way you define the sheaf on an open set to be a single vector space. Is that what that is up above?
Oh, so this local system thing?
Yeah, right there. So for an open set, f of u is a one-dimensional vector space.
Yes, in this example, f of u is a one-dimensional vector space.
And so a section is
going to be a vector in this vector space.
Okay, great, thanks.
Yeah, so here these local solutions are like vectors in a vector space. You can add them, you can scale them, and they're still in the same vector space. And then the stock is going to be the germs of local solutions. So yeah, so they also form a vector space, but there are different vectors than in here. They're equivalence classes of vectors of where you range over different open sets containing X.
Right.
Okay. Yeah, so that's a lot of definitions. And now I want to talk about intuition. So remember that locally constant sheaves are covering spaces viewed from below. So this is what I said last time. The top-down perspective is covering spaces, and here you have covering space Y and one global projection that goes down and covers X. And the bottom-up perspective is locally constant sheaves. Here you have a base space X, and then you're forgetting about what Y is, but you have many local sections. So the point of the bottom-up approach is to forget about the total space Y and just work with all of the local sections. And if you have the information of all of the sections, all of the local sections, then that gives you essentially the same information as the entire covering space Y above. So that's the situation with locally constant sheaves and covering spaces. And then there's an example versus non-example of covering spaces. So here on the left is a valid covering space. So my base space is R, and the total space is R cross C, where C is a discrete set with the same cardinality as R. And the projection map is just a projection onto the X coordinate. So we see that this is actually a valid covering space because the pre-image under this projection of any open set in the base space is just that open set cross times the discrete fiber. So that's what we need for it to be a covering space. And also the sheaf of local sections here, if you look at them, they are constant. They are locally constant. So that's good. But here we have something that looks similar. It's R2 with a standard topology. And this is not a valid covering space because if I look at an open set in my base space R, and then the pre-image of this projection map is going to be U cross R, and this fiber R is not a discrete space. So that's why it's not a covering space. It doesn't obey the local triviality condition of a covering space. And also the sheaf of local sections is not locally constant. If you look at a section on this open set, it's going to be some continuous map, and this need not be constant, whereas here they have to be constant. Okay, this example on the right is an example of a vector bundle. So for each open, if I look at it as a top-down perspective as a vector bundle, it looks like a projection where on the top I have a total space and the fiber over each point is a copy of R. So that's a vector space. And right, so that's why it's a vector bundle. Okay, now the intuition for locally free sheaves is that they're just holomorphic vector bundles on D viewed from below. So I want to say, what is a holomorphic vector bundle first? So it's a top-down perspective. Again, here on the left, I have the top-down perspective, a holomorphic vector bundle. So what I have is a total space E, which is a complex manifold. And I have P, which is a holomorphic surjection from E down to D. And D is a connected open set of my complex numbers. And what makes it a holomorphic vector bundle is that if you look at the fiber over each point, it has a structure of a complex vector space. And also, any point has a neighborhood E, an open neighborhood E, such that the pre-image of this neighborhood V under the projection map looks like V times C to the N, right? So it's going to be V times a complex vector space now. So that's going to be a holomorphic vector bundle. The pre-image of V looks like V times C to the N. So it's like this here. So that's a complex manifold. And what I'm saying is that a locally free sheaf, the whole definition that we gave above with the sheaf of O modules, and the fact that if you restrict E to some small open set, it looks like O to the N restricted to V, right? That whole thing is just the bottom up description of the same concept. So here I have holomorphic vector bundles, and then here I have locally free sheaves on D. And what is happening here is that I have my domain D. I'm forgetting about the total space, but let's just work with the total space for now. And right, remember that the pre-image of some small open set is going to be V times C to, here, U times C to D. So it's going to look like, the pre-image looks like this. And then what we're considering is the sheaf of holomorphic sections of this holomorphic vector bundle. So they're going to be maps from small open sets of the domain into this pre-image up here, which looks like V cross C to the N. So they're just going to be holomorphic, and they have to compose to the identity when you project down again on this open set. So I'm just taking a point here and assigning it to it some point in C to the N. You can think of V as like an indexing set. It's giving me a point in the space, and then c to the n is like a vector in c to the n. So a section of a holomorphic vector bundle is just going to be a vector field on this open set U. It's assigning to each point in the open set some vector in this in the pre-image. Right. Okay, so that's locally free sheaves are just holomorphic vector bundles viewed from below, and here we can write the explicit equivalence of categories between holomorphic vector bundles and locally free sheaves by taking a holomorphic vector bundle and assigning to it the sheaf of holomorphic sections of this holomorphic vector bundle. Here, HE restricted to V looks like the sheaf of holomorphic functions and direct sum restricted to V. Because why? Right, if I pick my open set to be small enough, like V, for example, the pre-image looks like V times C to the N, right? So then the sections are just going to be maps from V into C to the N. And maps from V into C to the N, they're just N tuples of holomorphic functions on V. So locally, this sheaf of holomorphic sections looks like O to the N. So the sheaf of holomorphic sections is locally free of rank N. Okay, so that's that. Are there any questions about locally free sheaves being holomorphic vector bundles viewed from below?
What kind of isomorphism is that between on the left when you define the holomorphic vector bundle between the pre-image and V cross CDN?
Oh, here?
Yeah.
So what kind of isomorphism is it? Let me see quickly. As complex manifolds.
Okay.
So there's an isomorphism of complex manifolds, pre-image of V, isomorphic to V times C to the N of complex manifolds.
Okay.
Also, over V, inducing vector space isomorphisms on the fibers. I guess. Okay, so I just read that from this textbook. But yeah, so here we're thinking about complex manifolds.
Nice. Okay.
Right. Yeah. Okay. So yeah. Any other questions? So the claim is that this gives an equivalence of categories between the category of holomorphic vector bundles on D and the locally free sheaves on D. Oh, so you were saying you're good?
Yeah, I'm good. I'm good.
Okay.
Where with locally free sheaves, the maps are the inclusion maps with this equivalence of categories that you're about to get to.
Repeat that.
You're about to talk about this equivalence of categories, right? So the morphisms of so there's morphisms of sheaves, or the morphisms on the right.
Right. Yeah.
Okay. Yeah.
Yeah, I didn't go too much in detail about how morphisms are mapped, but this is how objects are mapped. Okay. Yeah, the only thing I want to convey is that this is the top-down perspective, and this is the bottom-up perspective. So, okay. And then, so now I want to give the intuition for holomorphic connections or the connection maps. And so at this point, I don't have any more notes. So I'm just going to try to say this on the fly. All right. So here we have a holomorphic connection is going to be, remember, it's a locally free sheaf E and a connection map D for this locally free sheaf E. And so what this is just a notion of derivative for sections of holomorphic vector bundles. So remember I said E is a holomorphic vector bundle viewed from below, and del is taking sections, holomorphic sections of that holomorphic vector bundle and telling me how to take derivatives of that. And it's going to give me one forms or n tuples of one forms. So so let's just go back to the vector bundle R2 covering R, which I think is helpful to see what's going on, even though this is not the complex setting. Here, what we have is a base space R, and then I have a vector bundle over it. And so the fiber over each point is a one-dimensional fiber. So yeah, right. So it's a vector bundle. And the local sections are just these functions, right? So, and so they look just like continuous functions. And so we can take derivatives of functions. So that's the sense in which I want to talk about the other things. I want to look at local sections of vector bundles and tell you how to take derivatives of these sections. That's what E is going to, that's what del is going to do, right? Okay, so at this point, I don't have any notes, so I'm just going to try to say this, what's happening more generally. So this is just R cross R. So my pre-image is U cross R, but so yeah, so I have one-dimensional vectors at each point, and then right, so the derivative is going to be another function, but I can also just give you my connection map is going to take these local sections and give me one thing it can do is give me this one form df. And df is the one form that just looks at tangent vectors in my base space. And when you evaluate this one form on some tangent vector in the base space, it's going to give you the derivative of the function in the direction of that tangent vector. Right. So yeah, right. So this is how I'm taking a function, and the connection map is giving me a one form, which is packaging all of the directional derivatives into one operator. Right. Okay. And now if I want to talk about maybe, for example, I don't know, like, so I'm trying to think of examples on the fly here now, right? So I have R here, and maybe I cover it with R cubed. So this is R cross R squared. So over each point, my fiber of this vector bundle looks like a plane, right? And if I have a section of, maybe just pick some small set, I don't know. I can even just pick a global section because this R is fine. Anyway, so a section is just going to be a map. Okay, let's forget about local sections. Let's just talk about a global section. It's going to be a map from R to, and it's going to assign vectors to each point. right? So since I have a two-dimensional thing, over each point, I'm going to assign some vector, right? And to tell me how to take the derivative, so what I'm doing is for each point, I'm assigning to it some vector. So this is like a section of this vector bundle is going to be a vector field where the vectors have the dimension of the fiber. And so at each point in my domain, I'm assigning a vector inside of the fiber over that point. And then to take the derivative, a connection map is going to take these sections, which are just looking like vector fields, and it's going to give me a one form. So I don't know, maybe I'll call the sheaf of local sections, in this case, again, E, and here I tensor product it with this. So we know what's happening here. So E in this case looks like just holomorphic functions. So okay, the image here is real, but we can replace everything with complex numbers, and it'll be similar, I think. And on the other side, we said that the holomorphic functions tensor product with D is just the one forms. So, or right, my bad. This is holomorphic functions direct sum with itself. Because right, over each point I'm assigning a two-dimensional vector space. So the fiber is two-dimensional. So really, a section is like a pair of holomorphic functions, right? And then here, right? So I realize I'm mixing the R picture, the real picture, with the complex terminology, but hopefully it's clear what I mean. And since this is a free sheaf, like it's not just locally free, it's also free globally. On the other side, I'm just going to get pairs of one forms. So what I should do is take some section. So maybe I'll just use the letter S for section of this vector bundle. What this connection map should do is it takes sections and gives me a pair of one forms, maybe omega 1 and omega 2, right? And a specific example we can do is like, so this section is just going to be a pair of functions S1 comma S2, and a specific example we can choose for this thing is just going to give me the one forms associated to each of these coordinate maps, right? So each vector up here has two coordinates, and so when I write my section like this, I am implicitly identifying all of these tangent spaces, and I'm thinking not tangent spaces, all of these fibers. I'm thinking of all of the fibers as being a single vector space now, right? And this section is going to be a map from the real line to the single vector space. And instead of having separate vector spaces up here, I just have a single vector space, and so I can talk about pairs of functions like this. And that's only possible because I have a free sheaf instead of a locally free sheaf here. So I can talk about globally, I can write this section as just a pair of functions. Okay, I'll use the word holomorphic functions. And then, so these are the two coordinates of my function. So it's a pair of holomorphic functions inside of here. And then what I get is a pair of holomorphic one forms. So these are the differentials of the two coordinate maps. And yeah, what this does, the reason it's a derivative is because it's telling me how to take the derivative of this vector field or this section. What a one form does is it takes a tangent vector in my base space, so if maybe a small tangent vector here, and it operates on those tangent vectors. It takes tangent vector and spits out the directional derivative of the first coordinate of this vector as I move along the line along the tangent vector there, right? So I can feed as input any tangent vector in the base space to this pair of one forms, and it's going to give me the directional derivative of this section along that tangent vector. So in that sense, a connection map is just giving you a notion of derivative for sections of a holomorphic vector bundle, right? Okay, maybe, was that clear? I mean, honestly, to me, it's still confusing each time I explain it.
The question, we don't erase that. The question that I have is really, this section should correspond to a two-dimensional vector, right? And then from that, you're getting this pair of functions. So what's the
For
corresponding?
each, the section is mapping this real line or some small open subset of this real line to this total space.
Right.
And so for each point down here, it's giving me a vector in the fiber. So the fiber is two-dimensional. So for each point, I'm assigning to it some vector in the fiber.
And from there, where do you actually look at the functions S1 and S2 rather
Right.
than?
I think of each of these vector spaces. I can do this in this particular example because I think because this is a free sheaf. So I am just
You're using that
identifying.
isomorphism.
Yeah, I'm identifying each of the tangent spaces with each other. So I have a vector originating at yeah. Right. So it's kind of similar to what I did up here, right? I was, you know, what is a section up here? A section up here is taking a point down here and giving me a point up here. But a point up here looks like V times C to the N. And now I'm just forgetting about V and just looking at C to the N. So I get a map from V to C to the N. And being able to do that is identifying the fibers, right? So I have a different vector space at over each point in my base point, but then I forget about the fact that they are lying over different base points. And I'm just going to this vector space. So even though I had different vector spaces over each base point, I'm just thinking of all of them being the same vector space. And so I get a map, an n tuple of holomorphic functions. Right.
Okay.
Okay. Yeah. And so, right. Yeah, that also ties into the fact that why it's called a connection is because it's connecting these fibers. So we have different vector spaces, different fibers, and you have different vectors in each fiber. But if we can think of all of the fibers as being the same fiber, then I can actually take the derivative because I have a function or an n tuple of functions from my space to a single space. And then I can take the derivative. I don't know if that is clear, but okay. So what was the point of having this connection map? Well, Remember the first thing that we did here, we went from holomorphic connections to complex local systems. And the way we did that was we took a holomorphic connection and assigned to it the subsheaf of horizontal sections. So these are the sections for which the derivative is zero, essentially, right? Like I said, a holomorphic connection is just, this guy is a holomorphic vector bundle viewed from below, and the other guy is telling me how to take derivatives of sections of this holomorphic vector bundle. So that's what del is doing. And then in order to have that del f is equal to zero, what that means is that the derivative of this holomorphic section, this holomorphic vector bundle, is zero. And locally, that means that these sections are locally constant. So that is how we're going from a holomorphic connection to a complex local system, and getting in this complex local system, these are sheaves of vector spaces which are locally constant. And here, if I'm a solution to this differential, if you think of del as a differential, as giving you the derivative of f, then this is kind of like basically a differential equation as well, right? So I'm solving the differential equation where this notion of derivative is provided by del. Okay, so that's more intuition. And I'm going from this notion of a derivative on sections of this holomorphic vector bundle to this local solutions for which this notion, local solutions, or the sections for which this notion of derivative is zero, evaluates to zero. So they're horizontal because, like the constant functions which have derivative zero, right? They're horizontal or flat, right? Horizontal means derivative zero. Okay. Right. So I went from holomorphic connections to local systems, and the whole point of defining this notion of derivative del is so that I can ask the question, when does a section have derivative zero, right? And it, again, if we go back to the real picture, maybe in this same example here, to say that a section has derivative zero here would mean that when I identify all of these vector spaces by maybe forgetting about this axis, right? What it means is that derivative zero means that I'm just parallel transporting vectors between fibers. So I have a fiber here, which is a vector space, and I have a vector inside of there. And then if it's part of a section which has del s equal to zero, what that means is that as I vary the fibers, the vectors stay the same, or point in the same direction with the same length. And it's easy to see like we can actually see what's happening in this case just by a rigid transformation of R3. We're just translating this vector to the right, and that would be the parallel transport of this vector here. So in differential geometry, we talk about connections, and what they do is right, they let us derive sections of a vector bundle, and we can use the same notion ds equals zero to define parallel transport between fibers of my vector bundle. So originally, this concept of connection came up in the context of tangent bundles. So I may have, like, this is maybe my my base space is a sphere, and then my vector bundle is going to be the tangent bundle. So for each point in the sphere, I have a vector space, which is the tangent space at that point. So really, you can't identify these vector spaces. They're actually different vector spaces. At each point, you have a different vector space, and but there should be a notion of parallel transport here. If I take a vector in facing here, then maybe if I do a rigid transformation of the sphere, I should get a vector over here. I don't know if that's actually the parallel transport, but 1 second. Right. Okay. Sorry, I'm back. You're right. So how do you go from vectors? How do you transport vectors between different tangent spaces? Well, you need a notion of a connection, or so in differential geometry, we have what's called a Levi-Civita connection, and that's given by the metric, or maybe it's Civita connection. And this is given by a metric defined on your space. And so sections of the tangent bundle are going to be vector fields on your space. So here we have the sphere. And in order for, in order to actually define parallel transport between vectors of each tangent space, I need this connection, which is compatible with the metric, and then it tells me how to transport vectors between tangent spaces. Okay, so that's that. And right, the whole point of having, right, and also another example of a constant section or a derivative zero section would be, maybe you have a vector field on R2, right? And then this is covered by the tangent bundle of R2. So a section of that is just going to be a vector field in R2. And then it has derivative zero if it's just a constant vector field, right? So in that sense, it's also giving me parallel transport between different vector spaces. Now, okay, the vector space here, the tangent space here is a vector space with origin at this point, and the tangent space here is there. And so then it's a transport between fibers of this vector bundle. We need a notion of a connection as well. Right. So that's what connections allow us to do. If we have a notion of a derivative for vector fields, so when we have a base space X, and then we look at the tangent bundle Tx, so this is an example of a vector bundle, and sections of this vector bundle are just vector fields on X. And then we can say how to derive vector fields on X by looking at a connection, in particular the Levi-Civita connection, and then the ones that have derivative zero allow you to parallel transport between different tangent spaces at different points. Here, instead of looking at this particular vector bundle Tx covering X, I'm just looking at arbitrary holomorphic vector bundles. And I'm looking at sheaves of sections of those vector bundles, and then saying that the derivative equals zero is like a parallel transporting vectors between fibers of this holomorphic vector bundle. Okay, so that's good. Now let me go all the way back up, and right. I'm basically just saying the same thing over, but right. The holomorphic connection is E del, and then what we get is a complex local system, E del. So these are the ones that are locally constant. So this is a locally constant sheaf of vector spaces, and then to get the represent right. So that's basically what I talked about today. So this is going to be, this functor here is going to be an equivalence of categories. So that's the step between these two categories, holomorphic connections and complex local systems. Right. And the point is that this del allows you to parallel transport vectors, which you think of as local solutions. Okay. And yeah, parallel transporting local solutions, like analytically continuing local solutions. So if you analytically continue around a non-trivial loop, and that's how you get a finite dimensional representation of the fundamental group. Here, you want to if you have a holomorphic connection, then you look at the horizontal sections and local and parallel transport those vectors. So the horizontal sections, I guess you can look at germs of horizontal sections, and then those are vectors in the stock, and then you can parallel transport those vectors around non-trivial elements of the fundamental group, and that way you get a representation of the fundamental group. So here, right. Okay, right. So that's the Riemann-Hilbert correspondence. Hopefully that was clear. Are there any questions about it?
How is the author wanting to fit this into the context of the earlier chapter, or the rest of the chapter? What was the specific point about putting this in?
The Riemann-Hilbert correspondence, you mean?
I think so, yeah.
Right. So the Riemann-Hilbert correspondence is about this equivalence of three categories. Right. And the Riemann-Hilbert problem or specifically Hilbert's 21st problem is asking about taking, so I'm just going to copy paste from last time, is this. So what it's doing is it's taking, it's asking the question, can you go from any representation so the Hilbert's 21st problem is asking, can you go from any representation of pi1 of some domain? Let's say the domain is C minus finitely many points. And can you realize that representation as the monodromy, not group? You can think of the group as being the image of the representation, but let's just say representation. Can you realize this any arbitrary representation of pi1d as the monodromy representation of some linear ODE of the Fuchsian type? So Fuchsian means it looks, oh, what happened here? I think I need to delete this again. Right, okay. I don't know why this is a little bit weird.
I think you must have inserted holomorphic in your original. Oh, there it is.
I think this just got a little bit messed up. right? The point is that this is a you can write a Fuchsian differential equation as some matrix like this, f prime equals a times f, where a is an n by n matrix of holomorphic functions on D with maybe up to symbol or with up to simple singularities at at xj. So what I mean is that the order of a pole at each deleted point can be at most one of these coefficient functions inside this matrix. So this is a differential equation of the Fuchsian class. And yeah, what I wanted to say is that this Hilbert's 21st problem is really an array of problems. So I have maybe m here and n here. So n equals 1, 2, 3, 4, and m equals 1, 2, 3, 4. Let's see. All right. So one. So we like maybe you don't remember, but last week we talked about the 1, 1 case is when you have a single pole. D is C minus X naught, or just some deleted point. And you want to look at first order linear differential equations. And the thing that we got was that they are represented by differential equations of the form f prime equals f times alpha over z minus x naught. And alpha is just going to be what the non-trivial loop, or rather the non-trivial loop maps to e to the 2 pi I alpha, something like that. So we did solve the Riemann-Hilbert problem in this case, and we also saw how to, like, that it was possible to solve it for arbitrary dimension here. But in those cases, maybe I'll use a different color. What we got was not a differential equation like this. We got a differential equation like this. And so finding differential equations like this is harder because there are more differential equations that look like this. This is a subclass of this, right? So we were able to find differential equations like this that solve the Riemann-Hilbert problem in the case of the domain is still complex numbers minus a point. Well, specifically, we had complex numbers. D is the complex numbers minus 0. And then the representation is just taking this guy to some matrix M in GLN. Right, so it's arbitrarily assigning this, and we were able to find something that some linear ODE that had this as its representation. And the thing that we got was, I think it was f prime is equal to a times f, where a is equal to b times z inverse, and b is something that satisfies m is equal to the exponential of 2 pi I b, or something like that. So, and you can solve this guy using some, and I mean, there's more to say here, but I didn't really go into all of the details here. The point is that the Riemann-Hilbert problem can be solved in arbitrary dimension for one deleted point. And then I also computed how to solve it in all of these cases as well, we have one-dimensional representation of arbitrarily many deleted points, right? My domain is C minus x1 dot 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 xm. So I have m deleted points now, and the differential equation that I want is going to be the sum of alpha I f over z minus, or right, over z minus xi f. I believe this is the differential equation we want. And the representation is just going to be sending alpha j to some, I guess, e to the 2 pi I alpha j, right? Okay, so we also talked about this, all of this. And then, so the first case in which the Riemann-Hilbert problem is not known right now is the two case, m equals to n equals 2. So two-dimensional representations of the fundamental group of C minus 2 points. Can you write that as a ordinary differential equation and then as its monodromy representation? So this is the first case that we don't yet consider, and this is the case that Riemann worked on, and this is why it's called the Riemann-Hilbert problem, Riemann-Hilbert correspondence, because Riemann worked on this case. And this is the differential equation that you get here is called the hypergeometric. Well, if you choose the points, the two singularities to be 1, 0, and 1, and also a singularity infinity. I need to talk about that, but give me a second. Riemann worked on this, and the differential equation here is the hypergeometric differential equation. So it's the first case that we didn't really answer. And what is the connection between the Riemann-Hilbert correspondence, this triple of categories? I have here holomorphic vector bundles and connections on them. Here I have complex local systems, and here I have representations of pi 1. So there's this triple of equivalences. It doesn't really help answer this question, because what I want here is a global differential equation on the entire domain, right? Either like this or like this. What this gives me is this category was supposed to be the differential equations, but really the differential equations are some subset, or some, like, the differential equations, each of these differential equations here or here give me some object inside of this category. If I think about, right, I forgot to mention this, right? So I can, if I pick, yeah, right, the point is that locally, this looks like some df1, dfr, or n. So I'm representing my I can represent my holomorphic connection as some with some connection matrix. So I didn't explain this today, and I don't. Maybe I will explain this in a little bit. But the point is that each differential equation, or the point is that locally this connection matrix or this connection map is giving me a differential equation on locally on each small open set. And then the solutions to that differential equation are going to be the horizontal sections. And it's these different systems of differential equations are glued together in a way to give me this global connection map, right? That's what's happening on this side. But so that's why it's a locally free connection, or rather a locally free sheaf, right? But that so this is an equivalence between pi1 reps and the locally free sheaves. So this representation is only valid in some small open set, and it may change depending on which small open set you choose and how you parameterize that open set. Anyway, if I wanted a global representation as a differential equation, some object inside of here, if I want to say it's globally some differential equation instead of locally in some coordinate system, it is looking like a differential equation, then I need my object here to actually be free. I don't want it just to be locally free. I want it to be free. And that was the example that I had above when I had del of f is equal to, I think, df minus f over 2z dz, right? So here, right, so this formula works for any section over any open set in my domain, because my sheaf is free instead of just locally free, right? So E is O. In the example that I had at the beginning of today's lecture. So since it's free, that holomorphic connection is the same information as just a linear ODE. But if I want a global representation for like, I needed my locally free sheaf to be just free. So that's why the Riemann-Hilbert correspondence is not that helpful for Hilbert's 21st problem. It is giving me an equivalence of 3 categories, and one of them is inside of them I have the differential equations representing some of the objects inside of here, but there are more things in here which are not globally like differential equations. They're just, I think, locally. So that's my understanding. Yeah, this Hilbert's 21st problem is still needs more work to be solved in these specific cases, right? And so maybe I can say a little bit about this specific case that Riemann worked on, where we have the hypergeometric differential equation. Also, actually, maybe, okay. So I have like 9 minutes left. So I wanted to talk about a little bit about poles at infinity. So this differential equation, df over dz is equal to f over 2z. And this has a pole at infinity. Right, so I'm just gonna rush this because I don't have much time. The reason it has a pole at infinity is because if I do the change of variables w over w equals 1 over z, then dw is equal to d of 1 over z, which is, so I need to take the derivative of 1 over z, which is negative 1 over z squared times dz. And so that's what's happening here. And then I plug this in, or in other words, negative z squared dw is equal to dz. And then I plug this into my differential equation to see that df over negative z squared dw is equal to f over 2z. Wait, did I do that right? Oh, my.
That's not right.
Oh my. I mean, okay. Anyway, so what I eventually get is like this is going to be um right. Sorry. Maybe.
I mean, did you want to make the substitutions W equals 1 over Z in the original equation above?
Yeah.
So maybe just do that carefully.
Okay. Okay, so let me do, this is the same thing as Z equals 1 over W. Maybe this helps. Okay, so then dF over D of 1 over W is going to be dF over, so I have negative 1 over W squared dW. And so this is negative W squared dF over dW. And this is equal to dF over dZ, which is F over 2Z. And that's just F over 2 times W, because 1 over W is Z, right? So I have that, and then I divide by W squared on both sides. So dF over dW is negative F over 2W, right? Okay, so if I re-express this differential equation at infinity, using the change of variable Z equals 1 over W, then I see that this has a pole at infinity. Wait, is this right? Right, yeah. So a pole at has a pole
At W equals 0.
at W equals 0, which is Z equals infinity. Okay.
Right on.
So that makes sense. And so, and why is this? This is good for me because I want to think about representations of pi1 of now. I'm thinking of my differential equation as a differential equation as part of. So this is kind of why it's good to think about holomorphic connections being patched up by locally by differential equations, because here I have two different differential equations, but they're part of the same object, right? So some holomorphic connection on pi1 or the projective line over C. So I have some holomorphic connection over the projective line, and that restricts to a holomorphic connection on my domain. Or maybe, yeah, I don't know. My domain is still a subset of this. But now it like has solution, it has singularities. So now I have singularities at 0 and infinity. So this is good because if I look at the fundamental group of my domain, which is going to be the projective line, which is C union infinity, minus 0 and infinity, it's still going to be the same domain, C minus 0.
Right.
Right. So this still has a fundamental group of Z, which is good because, like, if I think about the complex or Riemann sphere, I have 0 and then I have infinity here. If infinity was not a pole of my differential equation, then I would be looking at representations of the Riemann sphere minus 0, but that fundamental group is trivial because it's contractible here. So the fact that there is a pole at infinity is good because it still means that my non-trivial loop is still non-trivial. So that's good. And so we can extend this Riemann-Hilbert correspondence to representations of things. Okay.
You're extending things to the form of the Riemann sphere minus points instead of C minus points.
Yes. And the point is that there is some kind of equivalence of categories there. And yeah, I'm not being too specific here, but anyway, the specific example we care about is this Riemann, the case that Riemann worked on, the hypergeometric differential equation. Oh, I wanted to say this is if you have singularities in C, and then you can also look at the projective line. And here, oops, I should probably.
So this, are you,
This
if
is
you're
the
saying that
dimension.
this is gonna be P1 minus 3 points effectively?
Yeah. So this is C minus x1 up to xm, and here we have the projective line P1C minus x1 up to xm. So I have instead now I have 2 points that are missing here and 3 points here.
Right on.
Right. So this case actually has a singularity at infinity as well. And so that's why in the book it's called the n equals 2, m equals 3 case. And the specific differential equation that we get here, let me just quickly say what it is. In this specific case, right, we have that the singularity is x1, x2, and x3 are 0, 1, infinity. So we choose them to be this way, or we do the change of coordinates to get it this way, and then we have a notion of local exponents at each singularity, and there are going to be pairs alpha. So alpha comma alpha prime at x1, beta comma beta prime at x2, and gamma comma gamma prime at x3. And what these things are, they're exponents so I don't really understand what this means. I'm assuming that what these local exponents are is that they are, if you look at local solutions around these points, then they look like z minus x, maybe around this point, z minus x1 to the alpha, and plus z minus x1 to the alpha prime or something, right? So you have a two-dimensional vector space of solutions. So the I think this is what local exponents means. It might be that this is just some part of the function, and you might have to multiply it by another function as well. I don't know, but so there's a notion of local exponents, and okay, I think this gets pretty complicated. I don't know if I want to say all of it. The point is that there is some hypergeometric differential equation. In some case, it looks like this. I just want to write down what the equation is. Y prime plus 1 plus a plus b z minus c over z times z minus 1 y prime plus a b over z times z minus 1 y equals 0. So this is the hypergeometric differential equation. So this is a special case of the things above. And the point is that we actually can write down what the monodromy representation of such a thing is. In this specific case, the monodromy representation of this differential equation is going to be so okay, so there are more assumptions, I guess. You need, oh, what are these A, B, and C's in terms of alpha, beta, and gamma, and alpha prime, beta prime, and gamma prime? Okay, I guess I'll just write it down what they are. So like, so this is when you set to the case alpha equals beta equals 0, gamma equals A, gamma prime is equal to B, alpha prime is equal to 1 minus C, and beta prime is equal to C minus A minus B. Okay, and then so that's where you get A, B, and C from alpha prime, beta prime, and gamma prime. And the monodromy representation associated to this differential equation is complicated. And if I get, so I'm just taking this from the textbook. If alpha minus alpha prime, beta minus beta prime, and gamma minus gamma prime are not integers, then the monodromy representation, well, you have two loops, right? You have C minus 0 and minus 1. So you have the loop that goes around here and the loop that goes around here, right? So maybe we call this gamma 0 and this gamma 1. So we have two loops representing the fundamental group or generating the fundamental group. And then the monodromy action is going to be the one that sends gamma naught to this matrix. And xp of 2 pi I alpha prime. So that's how it transforms local solutions. Now, when you walk around gamma naught and gamma 1 and goes to, okay, so this is more complicated. So okay, I won't write it down, but it's more complicated. It's like a ratio of things. So yeah, the point is that you can actually compute what the monodromy representation is. And yeah, so this specific representation is a special case of some differential equation that has that of second order with 3 singularities. And yeah, I guess it allows you to solve the Riemann-Hilbert problem in this case as well. Okay, so I guess that's the end of my talk. Are there any questions? I can stop the recording now.